Hello. So there's this idea in calculus that you can take a function and you can represent it as a power series. And so then it's a way to estimate, or actually exactly estimate. So you can just find a different representation for a function, and your power series and your function will return the same values when you input an x, when you input the independent variable. Now, specifically, I want to look at this idea of representing it by a geometric power series, since that's kind of the most basic, easiest way to find a representation for a function. And the goal of this video is to take that idea and kind of from the start and talk about a whole bunch of basics with it. So again, the claim is I can have this function 1 divided by 1 minus x, and I can say it is equal to this geometric power series right here, where I have a sub 1 and r is the common ratio. So more specifically, it would be represented by the power series where k equals 0, a sub 1 is 1, r is x, and to the k power. Because it's going to turn out that this is your a sub 1, and this is your common ratio. Okay, so I'm saying this function is equal to this power series representation, which is equal to x to the 0 plus x to the 1 plus x to the 2 plus all the way up to, well, I shouldn't even write anything because it goes to infinity. Okay, it's that power series representation. So I am saying that power series, I can evaluate this function at some number, maybe f of 0.5, and if I evaluate the function or evaluate the power series for x equal to 0.5, they're going to return the same value. Okay, now there's a reason I said 0.5 because that's in the interval of convergence for that power series. But just talking about the basics before we get to that interval idea. Okay, but this seems a little bit crazy, taking a function represented as a power series, a sum of a whole bunch of terms. In fact, the claim is even more than that. The claim is if I can get any function to be of the form, I need to say a divided by 1 minus r, I can represent it as an infinite geometric power series. So, in fact, I'm claiming I could have the function f of x equal to 8 divided by 1 minus x minus 2, and I can say, hey, I can represent that as a power series because I have represented this, or I've written in a form such that that is my a and this is my r. So I have my first term and my common ratio in geometric series speak. Why that form? Why am I saying if I can write any function of the form a divided by 1 minus r, I can call it a geometric power series? Why that? Well, that goes back to, we are now going to think about, well, what is the summation of a geometric series? Okay, so I want to take this step by step because I am able to say that this guy up here is equal to something. What is it equal to? Now, to figure out that, I want to not start with the infinite geometric series, but instead start with the finite geometric series. So k is 0, and I'm going to go up to n terms. A geometric series, we must remember, is when you're adding together a bunch of terms, where to get to the next term, you multiply by a common ratio. So that, in this case, is r. Sorry, this should be a k. Get my notation right. So what is this equal to? Well, it's equal to a sub 1 plus a sub 1 times r plus a sub 1 times r squared. It's like each time I'm multiplying by another r. And how many times do I do that? Let me do up to the third power. I'm going to do this all the way up until k is equal to n. So my last term is a sub 1 times r to the k. And I'm going to add all of those terms together. So what does that equal? Well, it equals sum s sub n is the notation we can use. Okay, but we want something more. What does that equal? There's got to be a formula for it, right? So a quick derivation of that. Well, here's the nifty thing. If I take all of this and I multiply it all by r, So I would get equal to a sub 1 times r plus a sub 1 r squared. Notice I take this term multiplied by r, it goes here. Take this one multiplied by r, it goes here. In fact, I'm going to do more than multiply by r. I'm going to multiply by negative r. Okay, so when I multiply by negative r, it just flips all these signs. So I'm going to minus a sub 1 r. This would be one term, and then this final term would end up being a sub 1 r to the k plus 1. And of course, sorry, I'm putting pluses. We should have minuses because I'm multiplying by negative r. Well, now what does that equal? It's no longer my s sub n, it's my negative r s sub n. And you kind of see how this r sub 2 goes to the r sub 3 and so on. And I'm going to add these two series. So this is the interesting work we're doing. We're adding full series together. Well, if I add together on the right side of this equation, I end up with s sub n minus r times s sub n. What do I get with the stuff on the left, though? Well, because of my multiplication at r and by negative r, this cancels, this cancels, this cancels. Everything is canceling except for what? Except for this a sub 1 and this negative a sub 1 r to the k plus 1 power. And okay, when I get here, that means I can rewrite this as a sub 1 minus a sub 1 to the r to the k plus 1. And sorry, I got a little bad with my notation. These k's were going to the kth term, so they should all be n's, which will match up my notation, so I have n plus 1. Okay, well, I'm interested in what s equals, like I'm looking for the sum. So on this side, I can factor out an s sub n. I'm left with 1 minus r. Can also factor an a sub 1 over here, like this. And then I divide by 1 minus r, and I end up with n. S sub n is equal to a sub 1 times 1 minus r to the n plus 1 divided by 1 minus r. Alright, so doing some nifty work, I end up with a formula for the sum of a finite geometric series. Okay, so that's a finite. Now let's take a look at the infinite, because thinking back to what we're doing, we're claiming that a function can be represented by the infinite geometric series. So now if I take the summation of k equals 0 to the n of a sub 1 r sub k equals a sub 1 times 1 minus r to the n plus 1. So I'm giving some space here because what am I doing? I'm letting this be infinite. So thinking calculus here, I'm letting the limit as n goes to infinity. Okay, I'm letting this be the limit. I'm taking the limit of both sides as n goes to infinity. What happens to this? Well, on the left side, if n goes to infinity, it's just, and let's slide up a little bit. This is just changing kind of how the summation notation looks. There's an infinity up top now. Okay, so n is going to infinity. And I get this. Now, maybe you remember from your work with geometric series that there is a claim that r, or that common ratio, has to be less than 1, or the absolute value of it has to be less than 1 for it to converge, for it to actually have a sum, and that's for an infinite series. That's because, let's say r is 4. So every time, let's say I start with 1, and every time I multiply by 4, well, if I add all of these terms up, it's just going to go to infinity. It's going to get really, really big. Okay, so it's just not going to work. But let's say r is 1/2. Then I'm at 1, 1/2, 1/4, 1/8. Notice how each term is getting smaller. So when I add them together, it's going to converge to a single term. Okay, because each term, in fact, the infinite term, it's approaching 0. So when I add them up, I'll actually get to a sum. Okay, so r has to be less than 1, or the absolute value of it. And that's kind of important for an intuition here as we let n go to infinity. So the only term being affected here is this right here. And what happens to it? Well, as n goes to infinity, I'm taking r to the infinite power. Well, again, let's assume r is 1/2. Like, what happens when I take a fraction to a really big power? Well, that's 1/2 to the 10th. 1 divided by something really big. That's something, and this is just something really, really small. Okay, that's just kind of estimate there, a pretty far off estimate. So it's something really small. Well, what if I go further? 1/2 to the 100th power. That's 1/2 to the 100th. That's an even smaller number. What's happening? As that exponent gets bigger, the result approaches 0 closer and closer, and that will happen with any fraction between -1 and 1. So as n goes to infinity, this whole value right here, it goes to 0. It approaches 0. Well, what does that leave me with in my answer? That leaves me with an a sub 1 times 1 minus 0 over 1 minus r, which is equal to a over 1 minus r. Hey, there we go. So we have seen this claim that the summation of an infinite geometric series is equal to a divided by 1 minus r. Okay, and now this may seem obvious, but let's flip this thinking on its head. Let's say I have something of the form a divided by 1 minus r. Well, that's equal to the summation of k equal to 0 all the way to infinity of a sub 1 times r to the k. Okay, that's saying if something is of the form a divided by 1 minus r, it is equal to the infinite geometric series. If anything is of that form, we can say it's an infinite geometric series and work from there and take that. I can change the representation. That's big. Okay, it's a little bit simple, just kind of flipping the orders from saying the geometric series is equal to a divided by 1 minus r, and flipping it to say that anything of the form a divided by 1 minus r is equal to the infinite series. So I'll bring this over to some open space, but I'm going to look at this function again. So that original function f of x equal to 8 divided by 1 minus x minus 2, I am claiming, because I recognize this is of the form of a divided by 1 minus r, it can be written as a geometric series. In fact, it can be written as equal to the summation for k equals 0 up to infinity, where a is 8, r is that x minus 2 to the k power. So it can be written as this. And I'm saying the output of the function and the output of the infinite geometric series is exactly the same for any x value. It's actually super clear once you kind of do this, and it's very obvious, it seems. So I can plug any x value into the function, and it'll be the same as plugging that x value into the power series. Oh wait, any x value? See, this is the thing where we are limited a little bit by our power series, because our power series only has a value for certain x's. It's called its interval of convergence. There are only certain values for x that it'll actually work for. And remember what we said? This is for an infinite geometric series. We said the absolute value of r is less than 1. Well, what are we saying r is? We're saying that that is x minus 2. So that has to be less than 1. Well, let's solve this inequality. You have these two. You got to split it up and solve. So you have x is greater than 1, but x is less than 3. So we have this interval of convergence of 1 to 3. So actually, only for x values between 1 and 3 does this series represent our function. So it is sort of limiting. Well, 2, it turns out, is the center of it. So if I plug in 2, I'm just going to get a boring 8. So I'm going to do something a little bit different, a little bit more exciting, and I'll say f of 1.5. Because see, what I'm doing right now is this true that I can evaluate the function and the power series at 1.5 and get the same thing? Well, if I plug in 1.5, I have 1 minus 1.5 minus 2. So I have 8 divided by 1 minus negative 0.5. 8 divided by 1.5, which is 3/2, so 8 times 2/3 is equal to 16 over 3. Okay, so that's my function evaluated at 1.5. What about my power series evaluated at 1.5? Well, let's get this out of the way a little bit. If I take this power series and I write it where x is 1.5, that's just substituting in 1.5 in for there as well. So that's 1.5 minus 2 to the k power, which is equal to the sum of 8 times negative 0.5 to the k. So I all of a sudden have this infinite geometric series. So what's the sum of it? Oh, I have the formula. I have the formula S sub n is equal to a divided by 1 minus r. A, which is 8, divided by 1 minus my r, which is negative 0.5, which is equal to 8 divided by 1.5. O, which is equal to 16/3. Hey, it works. But you're saying, well, duh, that's obvious. I mean, look at my series formula, my geometric series formula. A divided by 1 minus r. Well, that's exactly the same as like what I'm plugging over here in the function. Yeah, that's the thing. Like on the surface, it seems weird that a function is represented by the infinite geometric series. And you're saying, if I can just force any function to be of the form a divided by 1 minus r, as I did with this function, I can say it has this equal representation of a geometric power series? You're like, that seems crazy. Like, I can't just force stuff to be of that form. But if I can force it to be of that form, like it works out. Because we see that the formula for an infinite geometric series is equal to a divided by 1 minus r. So that's why we're saying if I have the function f of x equal to 4 divided by 2 plus x, if I can somehow force this to be of the form a divided by 1 minus r, I can say it can be represented by a geometric power series. In fact, you can do that with some interesting work. This is the same as 2 divided by 1 minus negative x divided by 2. And you can check that out. That is the same value. That's what you'll practice. You'll be doing like, how do I get a function in this form? Once you get it like this, you do see you have your a and your r. Hey, it's of a geometric power series. So I can say that this is equal to the summation from k equals 0 to infinity of 2 times negative x divided by 2 to the k power. And that equals... Okay, so you can write it as this geometric power series. So my goal with this video was to take something that, for me, on the first light, was like, that's just so simple, how does it make sense? So my goal is to take that simple idea, go in depth with it, make it complex, show how you get those formulas, and then go back to saying, yeah, so it can be just that simple, that if it's of the form a divided by 1 minus r, it is a geometric power series.